So now we've been able to sort of devise a system and we can classify stars from the hottest to the coldest, but it is important to address some fundamental questions. For example, how do different spectral classes fit together? Are they different evolutionary stages of sort of the same stars? Will O-class stars evolve to M-class stars or vice versa? Or perhaps would A-class stars evolve to F-class stars? More specifically, we've seen that the classifier is temperature, but what are their exact sizes and luminosities, and also how massive are those stars? I already told you that they also establish a ranking in terms of mass, but what are their masses? And furthermore, can we actually develop a simple tool or a plot or a graph where we could put all the stars in order to interpret them and understand their evolutionary stage, including all the way back to when they're forming? The modern answer to that final question is through an Hertzsprung-Russell diagram, or HR diagram for short. The diagram is named after these two guys, Enge and Henry. And before we explore it, perhaps we could think about a human comparison so that when we see it, it makes even more sense. Let's imagine that in the future, or perhaps the present of someone watching this, because in principle, these videos will survive for many years after COVID is gone. And let's say that in that future, you're actually sitting in Alexandra Square, all the movement is back, there's lots of your colleagues and other humans going about their normal lives. And let's imagine that for some reason, you start to measure people's height and mass so that you can try to understand the full population that's going around and whether there's any evolution from, for example, small humans to big humans and how they actually fit in a plot like this of height versus mass. Now, this is me just taking sort of data from stars to try to motivate the names that we're going to use for stars. But if we were to do measurements for humans, we'd probably find a few children running around that will have very little mass and be quite small. There'll be lots of adults that will follow some sort of relation between their mass and height. There might be, a basketball team coming along. They're really, really big. I think they're completely off the scale. I don't think any humans exist. For humans, we actually know and we have a decent understanding that a lot of these children will eventually grow up and they will become more massive and taller, and therefore they will move along this relation. Is this the case for stars, though? And do stars with low mass and, for example, low luminosity actually grow to become stars with high luminosity and large mass? First of all, we should think about what characteristics we actually want to measure and plot for a star. We could try to plot the size of a star and the mass, but the mass is something, as we shall see, that we can't measure yet. And even their sizes are not so easy to measure. The things we know how to measure include, for example, the distance, the apparent magnitude of a star, also the color or the temperature or the spectral class of the star, and also the luminosity or the absolute magnitude. And finally, we've also seen how we can measure the radius or the size of a star. And just for the sake of it, let's try plotting luminosity in solar units versus temperature. And we're going to plot temperature in a way that makes B minus V colors actually go up as we go from left to right. And because we want to do a pure astronomy plot, we're going to use log 10 in both axes. We do that, and on this side, you actually see stars which are the brightest stars in the sky. And on my other side, you see stars which have the largest parallax angles, or the ones that are closest to the sun. Focusing on this plot, we'll see that the sun is here. This is our reference. There will be plenty of stars that are actually colder and less luminous than the sun, but they sort of follow this relation, indicating that the colder the star, the least luminous a star is, but also that there isn't an infinite combination of temperature and luminosity. On the other hand, if we look at the brightest stars in the sky, the picture seems to be slightly different. We can see the sun here. Maybe this sequence continues all the way up to here, but there's some outliers, quite a lot of them actually. Stars that for a fixed temperature are way more luminous, and some of them, like for example Betelgeuse, for their low temperature, they're incredibly luminous. And as I pointed out, note that in this case, higher temperature goes with a more negative color, a bluer color. And because these plots have been done by astronomers, what they were actually measuring were colors, and therefore temperature will run in a positive way in this direction because color runs in a positive direction in this way. And this is also indicated here in the B minus V axis, which is the thing that typically astronomers will be plotting, while the y-axis, in this case, is luminosity. But in many cases, it may be absolute magnitude, which, remember, will invert the scale as well. Perhaps more interesting is if we try to combine all stars across the galaxy, measuring essentially their surface temperature with a color such as B minus V or B minus R, and their luminosity, and we can measure the luminosity with absolute magnitude and comparing it to the sun, so we have solar luminosity, we see that there's this clear pattern around here. There's this sort of relation between temperature and absolute magnitude or luminosity, but that on top of that, there's sort of a cloud of things which are really hot, but not that luminous, and also there's sort of two big clouds of things which for a specific temperature are way more luminous and super luminous. The other thing that we can already do is if we measure the surface temperature, because we already defined the spectral class, we can actually link it. So you can see it at the top, how spectral type goes from M-class stars all the way to O-class stars. And technically these spectral types only apply to the main sequence. So they're only referring to these stars that go along this relation. And we can also identify the position of where the sun is. An HDRI diagram can become way more useful and interesting if we actually link it and try to interpret it based on the physics that we already know. We've seen that because stars are very well approximated by black bodies, we can actually calculate the stellar radius by following this relation. Specifically in solar luminosities, this is relatively easy. And we'll see that because of this relation, we'll actually know how big a star is based on its position within the HDRI diagram. And perhaps the most insightful way to look at an HDRI diagram is to recover essentially what is the luminosity of a black body or luminosity of a star. We've seen and derived this in section 5 that the luminosity of a black body such as a star will essentially depend on its radius squared and the temperature to the power of 4. In an HDRI diagram, what we're actually plotting on one of the axes, the y-axis, is luminosity, and in practice, what we're doing is plotting log 10 of the luminosity. Therefore, if we take log 10 of both sides, we can actually see that what the HDRI diagram is plotting is something that depends on the temperature and also something that depends on the radius. What does this mean? It means that whenever we're plotting an HDRI diagram, what we are actually plotting is essentially the Stefan-Boltzmann law that you can see here, but in a log 10 form. And this will have a stronger dependence on temperature than it has on R. On the log form, this will have a slope of 4 with the temperature dependence and a slope of 2 for the radial dependence. Because of this, we can actually use our knowledge to actually identify the sizes of stars within an HDRI diagram. We'll see that essentially the radius is increasing in this direction. It also means that whatever these stars or objects are around here, they must be very, very small, essentially almost 10% or even less than the size of the sun. Obviously, the sun has a solar radius as expected, but we'll also see that this line, this relation that we call the main sequence, is actually not parallel to a line of fixed size, and therefore the spectral types that are the hottest are actually the largest. Some O stars will have solar radius of 10 or even more, and if we go down to the coldest spectral types, they will be the smallest. On top of that, we can also identify this cloud over here, and because they're quite red and they're very big, we call them red giants. And then we also have the supergiants, which are hotter but even more luminous. And finally, we call these stars around here white dwarfs, because in terms of colors, they're relatively white, but they're very, very small. And we'll see that actually, even though we call this the main sequence, stars on the main sequence will not evolve into any other star on the main sequence, but they can evolve out of the main sequence. Stars like the sun will eventually become red giants for a bit, and ultimately will migrate and become white dwarfs at the end of their lives, while stars that are more massive can actually become supergiants for a while before they actually go supernova and end up as a black hole, which obviously you cannot plot in something that has an absolute magnitude and a temperature.